Hey everybody, so today we're going to be going over topic 17, which is called, I think it's called Bayesian statistics. Yeah, Bayesian statistics. We're going to go over two things, two main things that I think are important concepts I really want to drive home out of topic 17. But before that, I wanted to show you all just a quick preview of what we'll be doing for the project and why and how this stats will all come together. So if you're not familiar with regression yet, not to worry, we'll get into all of that next week, starting next week. But I just want to show you all an example of one of the outputs that you will get. So this is an example of, I guess, you're predicting sale price with a bunch of other variables. Our regression project at the end of this phase will be predicting some continuous variable. The provided data set has you predicting housing prices using things like square footage, number of bedroom bathrooms, zip code, things like that. And so what we're aiming to do is build a model that can take in like number of bedroom bathrooms, square footage, things like that, and predict predicted house price. So that's what our project's going to look like. How does that relate to statistics? The model that we will be using, linear regression, which I'll talk about next week, is a statistical method. And so this is an example of an output that you're going to get used to seeing this over the next couple of weeks and also as you get into your projects. So don't worry about any of this, but I wanted to show you all that in this output, there are certain things that should look somewhat familiar. For example, standard error is something that you might have to interpret. T-statistics, so this is actually a bunch of t-tests being conducted. P-values, this probability is actually a p-value, and these are confidence intervals. So this is where I say that, you just have to interpret what these mean. You don't have to do any calculation because this is done in a single line of code. And you really just have to interpret what this means. And in a linear regression context, the interpretation is going to be slightly different than what we've been dealing with. And I will go over all of this when we get to linear regression itself. So for example, what you need to be able to do is, let's say these are p-values. And from what we've been talking about so far, p-values, the smaller, the better, typically. So if you see p-values, you see a lot of them are zeros. And if you see a p-value of like 0.130, what does that mean, right? Now we know that a p-value means that, and this 0.13 means that there's a 13% chance that whatever we're testing for is happening by random chance. So I'm going to get into much more detail when we get to this stuff, get to this stuff. But just so you all know, this is kind of what we'll be doing and how we'll be applying our stats knowledge. T-statistics, p-values here. Here you can see that there's an F-statistic, which comes from our ANOVA, which is what we talked about. Was that yesterday or 2 days ago? No, 2 study groups ago. Yeah. So just wanted to give you all like a sneak preview of what that's going to look like. So we won't be using statistics in the traditional sense that we've been talking about so far, with the exception of A/B testing that we did yesterday. This is how we'll be applying our stats knowledge. So yeah, I know there's been a lot of material so far in this phase, but really it's how you interpret these kinds of outputs, which again, we will get to. Also on that note, I wanted to show you all that I have the guideline stock for phase 2 project already put on your homeroom. Let me just double check. Yep, it's already on your homeroom, the phase 2 final project guidelines. This will come later, as you can see, like we won't really get into it until in a couple of weeks from now. But I wanted to first talk about sourcing your own data. So as I mentioned before, the provided data set is predicting the price of a house given, different characteristics or features of a house. You can definitely choose to get your own data for this. And you don't necessarily have to get your own data through an API or web scraping. I actually really recommend Kaggle. And I actually linked this is the search result page for regression data sets. Of course, not all of them are going to apply, but feel free to explore if you want to do something other than predicting housing prices. Most of these data sets that are on Kaggle are already fairly clean. And a lot of times they are already built for a machine learning task. And so you'll see that there's a few of them that will be made for regression. For example, If you want to do with Boston house prices, you can do that as well. Let's just go to a random page and let's see what we have here. Maybe we have car fuel consumption, perhaps. I mean, you'll have to go into it and look, but there's a bunch of different data sets on here that you can choose from if you don't want to do King County, which is what Seattle is in, if you don't want to do those housing prices. Some constraints that I'm going to set for this data set that you find on your own: at least 1,000 rows and at least 10 columns. So keep in mind that the goal is to predict a continuous variable. And yeah, use that as you're like looking for your own data. If you choose not to use the provided data set and you choose to like source your own data, you have to let me know, because I have to approve the data set first, just in case you go down any rabbit hole that doesn't eventually make sense, especially because now we haven't really talked about regression yet. Once you find a data set, let me know. You can already start cleaning your data even before you get into regression. So just in case any of y'all want to do that, you can. Any questions regarding this? All right. Of course, no need to rush into it. I just wanted to let you all know that this resource is here. Also, be careful because this Google Doc, you all have edit access, because at the end of this Google Doc, there's a whole like question and answer section that folks from like my last 3 cohorts, they've been leaving questions here. And so feel free to add your own questions when we get to the project, but just again, be careful that you do have edit access, so don't like change or delete things. All right. So to get started with Bayesian statistics, I want to do 2 main things. One, I want to walk through this problem, which if you remember my DS concept questions document, I'm going to go through this example over here, and I'm going to show you all what probability formulas that are good to remember, mainly because this probability question, I would say, is harder than all the ones that we talked about at the beginning of the phase, but this is actually, I think, out of all of them, the most common probability question that people have gotten. So numbers will be different, but way of solving the problem is the same. So what I'm going to do, I'm going to walk through the process of solving this problem. And the question that I have on the conceptual questions doc is it's the same problem, just with different numbers. So see if you can work it on your own. I haven't left that the answer here should be 33%. So I think a good method, a good way to practice and make sure that you know, or that you understand and internalize this process of solving this probability question is if you can replicate what I'm doing in a little bit with this question. So I'm going to set up this question that I'm actually going to write out. I'm actually going to go over the solution through my tablet. So let me quickly connect that. Okay, there we go. All right. So the question that we're going to go through is this diagnostic test. So this test is advertised as being 99% accurate. So what does that mean? It means that if a patient has a disease, they will test positive 99% of the time. And if they don't have the disease, they will test negative 99% of the time. So that's what they mean by 99% accurate. So that means 1% of the time, someone who has a disease, it will say that it's negative. And 1% of the time, if they don't have the disease, it will say positive 1% of the time. And then on top of that, 1% of all people have this disease. So the question here is asking, if the patient tests positive, what is the probability that they actually have the disease? So one common misconception, if you have this question set up, probability that you actually have the disease, people straight up will say 99%, which makes sense. That's kind of like how they phrase it. But if you're aware of like Bayes Theorem and just conditional probability, it will not work out to 99. You can actually see that the solution will come out to 0.5, and I'm going to work through that process. So let me share my whiteboard screen real quick so we can walk through this together. Before I do, questions on this setup? Okay, awesome. All right, so you should see a blank white screen. Let me know if at any point you don't. But what I like to do whenever I'm given a probability question is just write out the information that I have. To simplify, I'm just going to name events A and B. So there are two main things that are going on. One, a person can actually have the disease or not have the disease. And two, you have the whole 99% accuracy of the test. So two main events, we're going to call them A. The event A is the person has the disease. And then the event B is going to be that they test positive. So we're just going to call these events A and B for now. Now let's just take a look at some of the numbers that we were given and let's just lay them all out. So first, I think the easiest one to set up is the probability that a person has a disease independent of the test. So I know I can't share both screens at once, but one of the bullet points was that 1% of all people have this disease. So independent of the test, the probability that a person has the disease is 0.01 because 1% of all people have this disease. Okay, so what information do we next have? We have the accuracy of the test. So how we set that up is the probability, given that a person has the disease and they test positive, is 0.99. Because if the person has the disease, they will test positive 99% of the time. So therefore, the probability that given they have the disease and they test positive is 0.99. Conversely, because the test is 99% accurate the other way as well, conversely, the probability of the person testing negative, given that they don't have the disease, is also 0.99. And what we want to find out eventually is this conditional probability. What is the probability that given a person tests positive, what is the probability that they actually have the disease? So this is what we're trying to solve for. Questions so far? Okay. So before I get into solving the question, I want to lay out the theorems and the formulas that we have. So first we have Bayes' theorem, which is not important to fully remember. I would say maybe before, if you know that the job that you're applying for is going to be slightly more quantitative and they want, and like one of the things that they list is probability and statistics, then maybe yes. But I only memorized this because I did this for many years. But the Bayes theorem states that the probability of A given B is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. This is just a formula that I've memorized. So immediately, when do I think, oh, I got to use Bayes' theorem? Something unique about Bayes' theorem is that you have A given B, and then you also have B given A, which is pretty neat. You have the conditionals that are kind of flipped. I'm going to uncircle that. And a clue that I want to use Bayes' theorem for a probability question is that they gave me, oops, oh my gosh, I did not mean to delete that. Let's undo that real quick. All right. They gave me B given A, and I want to find A given B. So I know at some point I got to use Bayes' theorem. Another really quick segue of how Bayes' theorem was created, because I do think this is really neat to know. Bayes' theorem actually comes from the conditional probability formula. So conditional probability formula, conditional probability states that the probability of A given B is equal to the probability of A intersect B over probability of B. This is the conditional probability formula that we actually talked about back in topic 11. Again, not important to memorize, but I like to think of conditional probability as A given B. You can sort of think about what proportion of B is also A. That's just another way you can think about it. But how you get from conditional probability to Bayes' theorem is, okay, you have A given B is this A intersect B over probability of B. We can flip this around as well. What's the probability of B given A? It's again, the probability of B intersect A over the probability of A. So because these two top parts are equivalent to each other, we can just sort of rearrange this equation a little bit, and we end up with probability of A, probability of B given A equal to probability of B probability of A given B. And you just rearrange it a little bit, and that's how you get to Bayes' theorem. So that's just a really, really quick how you derive Bayes' theorem from conditional probability. So usually if you're given a question like this, you can pretty much skip to Bayes' theorem. I just wanted to show you all where Bayes' theorem comes from. So let me just get rid of this real quick. But any questions about anything I've said so far? Okay, sweet. Another equation that's going to come in handy, and I did talk about this if you remember the very last slide of topic 11. I don't expect y'all to remember this, by the way, but law of total probability is another pretty useful formula to know. I'm just going to call it LTP for law of total probability. And law of total probability states that the probability of A is equal to the weighted average of their conditional probabilities. So what that means is the probability of A given B multiplied by probability of B plus probability of A given B complement multiplied by probability of B complement. And at some point, we're going to make use of this formula as well. So let's go back to our initial problem that we're trying to solve. So we want to find the probability of A given B. Cool. Immediately right off the bat, we know, okay, we should use Bayes' theorem. So cool. Probability of A given B is equal to, we can just plug in Bayes' theorem, probability of B given A multiplied by P of A, probability B. Nice. So we have this, sweet. We also have this, nice. We don't currently have probability of B. So that's something that we're going to have to figure out. But as for now, we can plug in 0.99 multiplied by 0.01. We just have to figure out what the probability of B here is. So probability of B, it's not a conditional. So this is actually where we will use the law of total probability. So let's just flip this equation around. Now I know it says like A and B, so I'm just going to see if I can flip all the A's and B's around real quick. All right, so instead of this, it's going to be probability of B is going to be the probability of B given A times probability of A, and then probability of B given A complement, probability of A complement. So cool, we might have some more numbers now. So if we try and like sub in all of the numbers that we have, probability of B given A, cool, we have this. This is 0.99, this is 0.01. And then this probability of A complement, remember that complement is always 1 minus itself. So therefore, probability of A complement, because A was 0.01 from here, probability of A complement is 0.99. And then we have this last one over here, probability of B given A complement, which we don't currently have. We have B complement given A complement. So I know there's a lot of thinking that's going on here, but another thing to remember is when I talk about the probability of B complement given A complement, that's basically what proportion of A complement is B complement. Now, what if I were to think about this? What proportion of A complement is B? These sum up to 1. One way to think about it, let's just say that this circle is A complement. And part of this A circle, and imagine there's like something else that's going on here, but this is A complement. This whole circle is A complement. And this part is also B. This part will be B complement. So therefore, we know that these two sum up to 1. So therefore, even though we don't directly have this, we kind of do. This is basically 1 minus 0.99. So this is 0.01. So cool. At this point, we already have all the numbers that we need. So what we're going to do now is let's figure out the probability of B. The probability of B is going to be 0.99 times 0.01 plus 0.01 times 0.99. Sweet. So then we just have to plug in this into here. And you see that this multiple of 0.99 times 0.01 occurs everywhere. So therefore, if you like put this in the denominator, you can actually cancel them out and you end up with the final probability of 1/2. Cool. Does that make sense? Does anyone have any questions about this question? Okay. I highly recommend, I know there are a lot of steps here, and this is something that I feel comfortable talking about only because I've done questions like this a lot. And it's, I would say, like, if you want to put some effort into any probability question, this would be the one. So yeah, I would say try to replicate this process with the COVID test question that I have on the concept questions, just to get used to working out this math on your own. And usually when you're given a question like this, the 2 times I've gotten this question actually in an interview, one time they gave me pen and paper so I could work it out. One other time they told me, how would you work that probability out? And then I just had to say, okay, I would use a combination of Bayes theorem and law of total probability. To be very, to be honest, those positions that gave me those interview questions are highly technical positions, like machine learning engineering positions, and also like teaching positions like this job. So very likely they won't have you like work out all the math, but just in case, this is a good one to have in your back pocket. Right. Any thoughts on that? Okay. So yes.
I just want to clarify. So probability of B and not A, it's essentially, in this scenario, it's 0.99 for A and B is
Which are you talking about? This one here?
Yeah, this one, yeah, the one that's underlined right here.
Okay, yeah, because this is the one that we didn't get as part of the setup of the question, right?
Right.
So yeah, the thing that's going on here is basically that the probability of B given A complement plus probability of B complement given A complement equals to 1. So as long as this first part is the complement of each other, they add up to 1.
Okay. All right.
Yeah, this is something that, like, honestly, when I usually work this out, I like have a whole, like, I would divide my paper into half, and then on one side just write all of the probabilities that I want to keep track of, rather than, because I like erased a lot of stuff as I was doing this. I also actually have this written down on a notebook paper right in front of me. So I'm not doing this purely off the top of my head. I just wanted to show the thought process.
All right, no problem. Thank you.
You're welcome. Any other questions or clarifications? Okay, so that was the one thing I wanted to talk about. The other thing I want to talk about today is the concept of likelihood. So part of this topic is there will be a couple labs talking about maximum likelihood estimation, which is a very, very mathematically, it's a pretty abstract concept, but I think it is important in thinking about what modeling is all about. So I do want to go into like some simple examples, not simple, but I want to like sort of illustrate what we're doing with likelihood. So I'm going to clear this. And I'm going to just divide this into 2 sections. So far, everything we've talked about, even when we talk about statistics, we're really talking about probabilities. So on one hand, we're going to talk about probability. And then later, I'm going to compare it to something else called likelihood. I know in like English, these are sometimes synonymous, but in statistics sense, they mean kind of different things. So let's just recap probability a little bit. So let's say I have a normal distribution here. This is a normal distribution. And this distribution is normal centered at 20. And then let's just say that it has a variance of 4. When you have this kind of normal distribution, again, this is a PDF. Remember that this is a probability distribution function of whatever this is. How do you read probabilities off of a PDF like this? let's just say I had a data point over here, and this is 24. The probability of a value being 24 in this distribution, we would trace up, look at this point, and then you get some probability value here. So let me just make this a little bit clearer. Here, this is the probability, and then this is like whatever values you're talking about. So this is how you do read a PDF, right? One way of just representing this in mathematical notation is the probability that x is equal to 24, given that x follows a normal distribution centered at 20 with a variance of 4, is equal to this p1 value. That's how you read off a probability. And so assuming that we have this normal distribution, and that's the distribution of whatever values of x we're talking about, the probability of x being equal to 24 is this p1 that we got over here. We can do another example as well. Let's just say we have this point over here. Let's say this is 19, and then we trace up 19, and then we look at the probability here. Let's just call this p2. So then the probability of x being equal to 19, given that x has this distribution of 20 and 4, is equal to p2. And of course, the probability of something being 19 is greater than the probability of something being 24 based on this distribution, because 19 is closer to 20 than 24 being closer. 19 is closer to 20 than 24 is. Any clarifications on this? Because this is important to like understand before we go into the next thing. All right. So likelihood is kind of different. I like to sort of think of it as the reverse. So likelihood or probability, we're looking for the probability of a value conditioned on the fact that we know the distribution. Likelihood is different. Likelihood is we know the values. What is the probability of the distribution? Which sounds pretty crazy, but let me see if I can illustrate it in a way that makes sense. Let's use a different color. So let's just say we have these values of x. An example that I like to use, let's just say that I run a pound and I have a bunch of puppies, and I want to do some sort of study to figure out what is the distribution of puppy weights. Yeah, what does the distribution of puppy weights look like for the entire population of puppies around the world? But I only have a few puppies in my pound. So I'm going to try and make an inference based on my sample on the population. So I'm going to try and make some conclusions on the population based on my sample of pound puppies. So let's just start with one puppy. And let's just say that the one puppy that I have is 24 pounds. So 24 pounds, I have this one puppy that's 24 pounds. So like I mentioned before, likelihood is when you know your values, but you're not sure of your distribution yet. So, okay, let's just use the same distribution that we had before. Let's use this distribution of, and this distribution is normally distributed 20, standard deviation of 4. In that case, how I interpret likelihood is I can do a very, very similar thing of tracing up here, figuring out this value here, and this I'll call this L1, and you'll see why I use L in a little bit. So cool. What does this all mean? This is saying that the likelihood of x being normally distributed with parameters 20 and 4, given that I have my x being equal to 24, is equal to L1. And this likelihood value actually acts very similar to probability. This is actually like if you had this value of L1 of 24 on this distribution, it's exactly the same as P1, which is equal to P1. But that part's less relevant. So let's not talk about that yet, or we don't have to talk about that at all. So This is saying that what is the likelihood that the distribution is this distribution given that I have these points? And as you can see, the probability is right around here. Cool. So then this is just likelihood by itself. The whole idea of a lot of modeling is that we want to maximize our likelihood. We want to, which is why it's called maximum likelihood estimation. So to maximize our likelihood, what should our distribution look like? Which I know is a very abstract question, but let's consider this. So I only have this one puppy that has a weight of 24. Why would I guess that the distribution of puppies is centered at 20? Let's say I don't know anything about puppies other than the puppies that I have, and in this case, I still only have one puppy. If I only have this one puppy, why would I guess that the world's distribution of puppies is centered at 20? It makes sense kind of intuitively if I only have this one puppy to go off of, that I would guess that the world population of puppies actually looks something more similar to this, maybe something like this yellow line here. And as you can see, with this yellow line here, the likelihood, given that I have this, and 24 is right at the peak here, the likelihood has been maximized at L2. So another way we can put this is the likelihood that X follows a distribution of, let's just stick with the same variance for now, but centered at 24 and 4, given that we have our X equals to 24 is equal to L2. So we have maximized our likelihood based on the one data point that we have. So this is what we call maximum likelihood, because likelihood is maxed out at this value over here. Any questions to clarify what we've done at this point? Okay, awesome. So we made this conclusion that we can maximize our likelihood of this being the distribution of all the puppies in the world by centering our distribution at 24. So cool. So let's just say, okay, I had one puppy first, but then more puppies come into our pound. And then we slowly get more and more puppies. So here we have our 24 puppy. And then let's just say that, oh, okay, I got a puppy that's like 23, maybe 22, a bunch more that are around the 22, 23 range, maybe a couple very small puppies, maybe a couple large ones. But let's just say that we have like 20 new puppies, and then we end up with our data points looking like this. So instead, it makes sense that we want to shift our distribution. We want to shift the most likely distribution. So let's get rid of this yellow line for now. So the way that you deal with maximum likelihood is if you have multiple data points. Let me draw this curve real quick. Hopefully it looks nice. Okay. So maximum likelihood, we want to maximize the sum of all the likelihoods. So now that we know we have more of these puppies, it makes sense that we want to center our distribution around where we have more puppy weight. So there's going to be a bunch of points here, and then fewer as we go out to the edges. So what this means is, and let's just assume that this new yellow curve has a mean of, let's go with, I don't know, 22 and then 4. So this is just saying that given that I have X equal to, and X now I have multiple X's of, I have a bunch of values ranging from like 20 onwards to like 26. Let's just say I have all these values. I maximize my likelihood at X following a distribution of 22 and 4. And so we've maximized our likelihood with this new yellow curve. Questions about that? Okay, so why this is relevant is because this is what we're doing with modeling as a whole. We're given a bunch of data points and we don't really know about the patterns of it straight away, but we want to kind of figure out what kind of curve fits our data best. And that's exactly what we're going to be doing for linear regression. We're going to figure out what is the best formula or what is the best model, what's the best line that fits through all of our data points to maximize the likelihood of our data. Because let's say that I assume, and let's like backtrack a little bit. All right, let me just, okay, never mind. I'm just gonna use a different color. Let's just say that I have these green X puppies, right? Like I have all these puppies that I got here that are centered at 22. And I make the incorrect assumption that doesn't maximize likelihood that the distribution of puppies is at 24. Let's just say I made that assumption, which is incorrect because it does not maximize likelihood. You can see that it becomes more dense here, very not dense here. Here it's a lot less dense. So that's an incorrect assumption. So the likelihood that X follows this 24 of 4, given that we know all of these X's of 20, 26, so on and so forth, this likelihood is going to be less than this yellow likelihood. And you can sort of guess that there's going to be some serious implications to doing that. If we made the assumption that it follows this distribution, if we want to maybe like, I don't know, make some decisions on how big our puppy cages should be, maybe we just estimate incorrectly. I would say the math going behind like figuring out what the best distribution is not super important, but there are mathematical proofs out there that show that, let's say you have this sample, right? Let's just assume that all these puppies, let's say I have like 50 puppies here. A good, the most accurate guess that will maximize your likelihood of what the population is basically the mean and standard deviation of your sample. So the math behind that is not important. What's more important here is that the whole concept of modeling is that we want to find the best curve or model or line that fits our data, that best represents our data. And that's kind of what I want to drive home with the concept of likelihood. Cool. Hopefully I didn't lose you all. But these are the main things I want to talk about today. Any questions or thoughts? I understand that this is super abstract. On our channel, I'm going to send out the specific StatQuest videos that I think are really well done that explain this concept. But yeah, any questions?
Go ahead, Mo.
Oh, so just, I mean, correct me if I'm wrong by saying this, but would the maximum likelihood estimation, is it fair to say that it's sort of conditioned or based on the number of values that are currently in the data set? Is that fair to say?
Yeah, absolutely. So I started with one puppy, right? And with that one puppy, my best guess was actually this blue curve at 24. But then as I got more information, I update my belief that, okay, yeah, given that I now know what more puppies' weights are like, I can shift that, okay, yeah, it makes more sense that the population should be a little bit on the lighter side.
All right. And would you, is it correct to say like probability, based on the examples you gave, it seems like variance has more to do with probability and likelihood has more to do with mean? Is that, or is that like?
Not really. Actually, both of them are related to, both mean and standard deviation, both mean and variance are related to both of these. It's easier to explain it with mean, but you can also kind of do the same thing by adjusting variance. Like, given this distribution, I'm just gonna like draw a bunch of curves. Like, let's say we say, okay, the mean is at 22, but now that we set our mean, there are ways to calculate this, and it's very math heavy and it's not important for us at all. But there are ways to figure out that, okay, if the mean is at 22 here, right? Is my curve the yellow curve? Is it more like this red curve here? Is it more like this curve here? Again, it's the same. It's really just by adding up all these likelihoods as well and figuring out which maximizes it. So yeah, standard deviation also plays a part in this. It's just a little bit more abstract to talk about standard deviation. But yeah, you can actually adjust different variances to see where your likelihood is maximized.
All right, thank you.
Mhm. You're welcome.
So my question, I guess, is aside from the normal, then this is kind of the same process when using like the Poisson or the like exponential and other distributions. Like we're looking for the shape of the data and then use one of the other distributions to estimate the mean and the standard deviation of our data. Is
That's
that kind
correct.
of
Yeah.
okay?
Yeah. So earlier when I said that we can use the mean and standard deviation of our sample to infer what the mean and standard deviation of the population, and that is for a normal distribution. It's actually different for other distributions. So that's good clarification.
Okay. All right. But basically, like if the distribution is shaped like, I guess, half of it is on one side, half of it another, then we'll just use like the Bernoulli formulas to get basically the same L1, L2, and et cetera, that you have here.
Correct.
Okay.
Yeah. Yeah. Any other questions? Because I do want to talk really quickly about how this will apply to linear regression.
I'm good. Thank you.
You're welcome. Okay. So let's see. Should I keep this or should I get rid of this? Yeah, let's get rid of this. Okay. So the whole idea of linear regression, which we're going to get into starting with the next study group. So I think this will be a good preface. So let's just start simple. Let's just say we want to predict height based on weight. And the way that we're going to do this process is we're going to just collect some height and weight combinations. And as you know, height and weight can really, really vary. So let's just say that there's one guy here, one guy here, one here, one here, one, like just a bunch of points here. And these all make sense because they're not directly going to be on a straight line. So our goal is to, given a person's weight, predict their height. What we're going to do is, if you're familiar with like straight line math, there are two things that we can adjust. And with linear regression, the goal is to fit a straight line that can best represent as much of this data as possible. So with a straight line, there are two things that you can adjust. One, the slope of the line, like is the line going to be like this? Is it going to be like this? Is it going to be like flatter like that? That's one thing that we can adjust. We can do that. Another thing that we can adjust is how high or low the line is, right? It can be like this, like this, like this. Imagine they all have the same slope, but which one is the best? So this is kind of similar to my maximum likelihood estimation because we want to figure out what line will best fit most of the data. And we'll get into more of the math of that later on. But the whole idea of linear regression, and this we're going to later also expand this to a bunch of other models, is finding out the best line to represent this data. So let's say we have this line here. And then specifically for linear regression, you can actually come up with a formula. So let's just say that the formula here is height equals to, I don't know, I cannot think of a number. Let's just say it's 3 times weight plus a certain number, plus, I don't know, 2. So given this formula that we've created, which is similar to that like curve that we created, given this formula, we can sort of apply this formula to all other, if we're given any weight of a person, we can try and predict their height. And therefore it's important that this formula is making good inferences on the population. And we're gonna get more into this next week, but that's how it connects to modeling, because this formula has to be fairly accurate, right? Like I was saying earlier, if we incorrectly guess our distribution of puppies, we can be buying the wrong size cages and stuff like that. We don't want to incorrectly make predictions. So using this formula that is based off of this data, they're saying that, okay, if we know a weight of a person, just plug that in and we'll get height. We'll get more into this another time. But similar to MLE, and also I know that gradient descent was in your pre-work a little bit. Gradient descent, which is something that we're not going to talk about this phase, but we will talk about it at the end of the next phase, is the process of adjusting this line to find the best line. So usually you start off with like a really ill-fitting line, like, oops, sorry, let me just. So usually you start off with like a really ill-fitting line like this. Let's just say you start with a straight across line. The process of gradient descent, which we'll get into next phase, unfortunately not this phase, is okay, we're gonna slowly tilt the line back and forth until we get something that fits nicely. So let's just say slowly you're like, okay, we're just gonna increment the slope by like 1 degree at a time until we get to a point where, okay, yeah, this line looks like it fits best. And then you can also do the same thing with like adjusting how high and low the line is. I'm getting into way too much detail on this tangent, but hopefully it drives across that the whole point of modeling is finding the best model or distribution to fit data that you're given, because you don't really know how things are distributed in the population, but that's what modeling is all about. Hopefully this will offer some intuition when we get into our modeling next week. But yeah, any questions based on this? All right, well, that's all I had to share for today. Next week, we finally get into our linear regression. I will say that if you are a little bit behind on the stats material, once we get to linear regression, I want you all to just stop wherever you're at with the material on stats and go straight into regression. A lot of the stats stuff, as you know, as like with my example that I showed earlier, a lot of the stats stuff is good to know for theory, but it's really all about how you interpret it. So I will talk about exactly how you interpret stats in a linear regression context. So I highly, highly recommend that wherever you're at, once we get to topic 18, just skip whatever and get straight to topic 18. And usually, as long as you've made it through like the first couple of topics in the phase and skip straight to 18, you're usually still okay. So let me know if anyone has any questions related to that. But I will also remind you all when we start topic 18 that everyone should just shift their focus onto that material instead of the other stat stuff. Cool. Any final questions to close out?
Yeah, I had a general question. What is probability, which is used more in terms of statistical analysis, probability or likelihood?
So in statistical testing and statistical analysis, probability. We technically modeling uses likelihood a lot more, but it's usually something that's done under the hood. A lot of these like algorithms that we'll talk about, they are formulated in a way to automatically maximize likelihood for us. So technically, yes, likelihood is the underlying thing, underlying thing that of all, it is the underlying concept of all modeling, but we don't really interact with it directly. But it's just a good thing to keep in the back of your mind as we're going through a lot of these processes. And as we get to them, I will like call back to these things as well.
Thank you.
You're welcome. Anything else? All right, then. Well, have a good rest of your week, everybody. I'll talk to you all at your one-on-ones. But if there's nothing else, I will see you all back here next week. I'm so excited to finally get into some machine learning stuff. All right, then. Have a good rest of your day, and let me know if you all have any questions at any point of time.
Thank
All
you.
right.
All right.
You're welcome.
Thank
Bye.
you.
Bye.